Okay, so here's where we were last time. We were talking about a pretty surprising way to solve differential equations. We made a seemingly nonsensical definition of something called a matrix exponential, and then we started solving differential equations with it. It's crazy. It's hard to imagine this would work. Let me just remind you, though, we have already done something not terribly different, right? We defined exponentials of imaginary numbers. That's kind of equally nonsensical, really, if you think about it, right? Maybe we've got a little bit more familiarity with that. You saw it earlier in your lives. You're more likely to just kind of accept, yeah, okay, I guess that's a thing. But on its face, it's a kind of a crazy definition, and yet you make a crazy definition. You observe the resulting algebraic properties that come from that definition, and you can use that to solve problems. And in fact, we used this idea of imaginary exponentials to solve differential equations. So this is not terribly, structurally it's not unprecedented, right? That something like this would work. Okay, so just a reminder of what we did. We were looking at a differential, wrong mode. Looking at a differential equation like this one. The matrix here, I gave you some critical arithmetic from which you can reasonably infer a Jordan basis. Now again, you're not responsible in this course for how to find a Jordan basis from scratch. That's a hard problem, right? But in examples where there's strong supplemental information given, such as this free arithmetic, it's pretty straightforward. It's just a matter of keeping track of which matrix is representing the transformation with respect to which basis. And not hard to persuade yourself that the one on the left is the one whose columns are the Jordan basis. And as we saw several pages back last time, you just multiply the Jordan basis, a Jordan basis, times this matrix exponential thing. And it all comes together and everything works. And that furthermore, we can evaluate these things with this formula. And we went through this, the details of this last time, as how to use this formula to explicitly solve for these functions. So that basis vector goes to that one, and then likewise this becomes that, and this becomes that, all straight out of this formula right here. Okay, so that's where we ended it last time. So quick reminder. Where did all that come from? Ultimately, that all came from understanding what this A minus lambda I matrix does to Jordan basis vectors. And looking at the matrix J, looking at a single Jordan block, we were able to conclude the following. Right? That what A minus lambda I does to Jordan basis vectors is a real simple pattern. It turns a Jordan basis vector into the previous Jordan basis vector. Unless you're talking about an eigenvector, in which case A minus lambda I sends it to 0. Okay, so this is the, all you need to know about what A minus lambda I does in the context of what I'm going to call that block. Now let me remind you, when I say that block, this block corresponds, of course, to certain columns. Those columns are telling you about certain basis vectors. Right? So this little diagram here pertains not to the entire Jordan basis. It pertains only to the Jordan basis vectors that are associated to that block. Right? We apply these formulas one block at a time because the rules change when you get to the eigenvector. Right. So I want to show you an example now where this actually becomes relevant. If we look back at the first example that we did, notice in this Jordan form, there is only one Jordan block. So there's nothing to worry about. Yeah. Right. But let's look at this next example here. Here's a Jordan block. A Jordan form. And notice there's 3 Jordan blocks. Let's look at that first Jordan block. This Jordan block is associated to certain basis vectors. And again, how does that work? Well, this block is clearly associated to these 2 columns. Those 2 columns are telling me about the images of those 2 vectors. Okay. This second block, associated to those two columns, the third and fourth columns, you might call them, those are telling us about the images of the third and fourth basis vectors. And then lastly, this block, fifth column, fifth basis vector. So we get separate little diagrams for each one of these. So, for example, this is what I'm going to call A minus lambda I does to V1 and V2. V1 and V2 being the vectors associated to that block, they're related by one of these diagrams. Now, the matrix that relates V1 and V2 by way of this little diagram is A minus lambda I. Wait a minute, what is lambda? Lambda is the eigenvalue for this block. For this block, the eigenvalue is 3. So you notice this is A minus 3I. Okay. On the other hand, let's look at this next block. This next block involves those vectors V3 and V4. This is the diagram then involving what A minus lambda I does to V3 and V4. A minus lambda I, what is lambda? Lambda for this block is 4. So A minus lambda I means A minus 4I. Okay. All right, and then likewise for the last one. Okay, so let's evaluate a matrix exponential on one of these Jordan basis vectors. I'm going to do it on one of them where it's kind of interesting, and so let's do V4. Let's talk about what is the matrix exponential e to the xa times V4. Right, and I'm going to be using this formula up here. Here is our formula, and you know, it's the pattern in the formula. The pattern in the formula is, we've got, e to lambda x up front. We've got this pattern of 48 of Taylor coefficients, 1x, x squared over 2, the usual Taylor coefficients. And then the rest of the pattern is to observe that the vectors are, start with your given Jordan basis vector, and then just keep moving backwards through the list of Jordan basis vectors. Here's where you have to remember, for that given Jordan block, right? Remember, you stop when you get to the eigenvector, whichever is the first Jordan basis vector associated to that block. This is the one where you stop. Not the first basis vector overall. The first basis vector associated to that block. So, applying as such, here's our little diagram. V4 is part of that blue block. So we're looking at this diagram, right? And I can write down then, well, in fact, I already have it written down. There's a V4 term. There's a V3 term. V3 is an eigenvector, and there we stop. And what a lot of students get wrong on this is they just kind of, hey, the subscript just keeps going down by 1. We'll do V4 and then V3 and then V2 and then V1. And they go all the way down to V1. Those vectors are associated with a different block and are just not involved in this diagram. They just don't, they're not involved in this equation. Okay, so be careful with that. Make sure to apply the that above formula appropriately. Stop when you get to the eigenvector. And other than that, everything else in this example is, structurally equivalent to the previous example. Yep.
When we either use this method or the other method, does it matter which one we use? Do we write the first part?
It depends on. Sometimes in the statement of the question, I might tell you I want you to do it a certain way, and of course, anytime during an exam, if I instruct you, don't use the following method, or be sure to use the following method. Use the following technique. If there's an instruction, then of course you have to do that. But outside of commands in the exam. In your free time, how you solve these equations, use whatever is most convenient for you, right? So, I think this is a pretty good one. right? Because it's just very, like, write it down. The back solving's got a lot of effort that goes into it. I will say that, give me 2 seconds. I will say that that even though this is very convenient for situations like this, all of this back solving business, well, more to the point, this strategy, the conjugating, the attempted decoupling, as a strategy, structurally is very important. So, this construction right here of a conjugation, this appears in math in lots and lots of places other than this. So this is, you might say, a template for a strategy that solves lots of problems, not just, first order systems of constant coefficient equations. So this is a big deal for a lot of reasons. Definitely want to make sure you understand this. Yeah. Right. Okay, you had a question.
When you're using this method, like the one you just showed,
yeah.
Can you just simply cite for the
yeah, totally. I mean, if you want to see how to write it down, I mean, you can see how I wrote it in previous semesters exams, and I can't see my thing. Here it is. There it is. Zoom out. Something along the lines of what I've written here is plenty sufficient. Yeah. So yeah, you don't have to like rederive this formula every time or anything like that. Yeah, you can just use it. Yeah. Okay, so on to a new thing. This is gonna be a very low on linear algebra day. It's gonna be a very heavy on differential equations day for the rest of today anyway. And we're going to go on and talk about the non-homogeneous case. So remember, structurally, this is just like we did in Chapter 4. In Chapter 4, we talked about, framework and strategy, and, we proved some theorems and that kind of thing. And then we talked about the non-homogeneous solutions. We talked about the homogeneous solutions first. And then after that, we talked about non-homogeneous solutions, because general solutions are just particular plus homogeneous. Okay. Same thing here. We've now finished talking about homogeneous solutions, so we have to talk about non-homogeneous. How do we find particular solutions? I can't seem to circle that correctly. Yeah. What did we do in Chapter 4? In Chapter 4, we guessed. Now, we eventually honed that into a highly educated, planned structure of guessing. But pretty much the idea of 4.3 is take a guess, leave yourself some fudge factors, and then plug it in and kind of work out what those fudge factors, aka undetermined coefficients, have to be. Okay. We're going to start with something different here in Chapter 6. We're actually going to derive an explicit formula for particular solutions. And this works out really nicely. I'm going to start off in the single variable case. So it's this sort of the scalar valued case. We'll get to the vector valued case in a couple of minutes, but I think there's something kind of nice about starting with the single variable case. If you look at a homogeneous differential equation, neat observation, this always works in that differential equation. Even if A is not a constant, even if A is a function, as long as it's continuous. That always works. That's kind of a neat observation. Whatever, that's worth. So here's what we're going to consider from that, and that is, and let's start with back to the homogeneous case here. In this homogeneous case, this function has the feature that when you plug into this equation, it balances. The left side, the right side end up giving you exactly the same thing. The action of multiplying by A is the same thing as the action of taking the derivative. Balance. Okay. All right. So, by the way, notice, same thing still works if you multiply by a constant. Still works. Same thing. Okay. All All right, so here's the new case we want to consider. What happens if I put this G term in here? Now it's out of balance, right? There's that which was on the left, that which is on the right. Now these are no longer equal because, well, there's this extra term here. So here's the idea. This is just a strategy. This is wild speculation. I have no strong reason to believe, I have no strong reason that I can persuade you of right now that this is going to work other than, maybe you trust me. What if I take this thing that used to work, it used to balance both sides, and let me just fiddle with it. Let me tweak this previous solution, and I'm going to hope to tweak it in such a way as to balance off this new term on the right-hand side. Maybe. It seems like something that can conceivably work, right? So that's the idea. The way we're going to tweak this solution is instead of multiplying by a constant, we're going to multiply by something that's not a constant. And of course that will change, how that our new function now, how that participates in the equation, because, I multiplied by a non-constant thing. There's derivatives. It's clearly going to mess it all up. Hopefully, doing that will mess it up in just exactly the same way that this G messed it up. That's the hope. Okay, so here we go. We're going to take this thing and we're going to shove it into there and see what happens to the equation. The equation turns into this. Notice we've got to take a derivative of a product, so let's use the product rule. The product rule gives us that. No big deal. And now, notice all that's really happened is because I put that V in there, I have kind of a new term. Right? I mean, in some sense, this is what was already there. There's M prime equals AM. I already knew that M prime was equal to AM because M was a solution to the homogeneous equation. So that's the old news. And you can see we've actually kind of, we've got daylight at the end of the tunnel. We've got this G that messed it up on the right-hand side, and now we see how V correspondingly messes it up on the left-hand side. And let's just see if we can strategically figure out how to pick V that makes these actually equal to each other. So, said differently, we're going to cancel those. And that leaves me with this. Solve for V. And there you go. There's your V. That's how you tweak your previous homogeneous solution to get a particular solution. In other words, that is the thing that you multiply by M to get your particular solution. So here is your particular solution. And that works just fine. And it's an explicit formula. It's pretty handy. All right, what do you do if it's vector valued instead of scalar valued? I wanted to go through the scalar valued first because I think it's a little bit easier to follow the strategy. So here's our homogeneous case. Vector valued homogeneous case. There's the homogeneous equation. Here's your matrix of solutions, by which, of course, I mean I've got a bunch of columns which individually satisfy that equation. So, a bunch of columns. Okay. All right. Loosely speaking, I'm going to say that M satisfies the equation, which it kind of technically does if you think about it. If you were to plug in this entire matrix in the place of where Y is, well, we're going to take the derivative up there. The derivative I would compute as if I were computing the derivatives of the individual columns. Right? What would happen if I multiply A times this matrix M? I remind you back in chapter 1, different points of view on matrix multiplication. It's the same as multiplying A times individually these individual columns. So you might say one column at a time M works, and therefore M itself works. So again, M prime equals AM. Just like in the scalar case. Okay. All right, let's set that aside. Here we are again. Let's look at the homogeneous case. This works. Everything's in balance. I can multiply by a constant. Let's call that constant C. Wait a minute, that could even be a vector. Right? I can multiply this matrix times a constant vector because all this is a fancy way of taking linear combinations of those columns, which are homogeneous solutions. So m times any constant vector is just a linear combination, which we know gives us more homogeneous solutions. So I can multiply by C, and it still works. Again, we find ourselves then wondering, well, what happens if this G term shows up? Now everything's out of balance, right? It's got this extra stuff on the right. Maybe, I speculate, maybe if I tweak this in some way, if I fiddle with it, maybe I can fiddle with it in such a way that other unbalancing terms show up that will cancel with this unbalancing term. Again, it's pure optimism that we hope that we can do this. But anyway, it worked out in the scalar case. Let's give it a try. Hopefully it'll work. And again, the way we're going to fiddle with this is we're going to turn that constant into a non-constant vector. So we're going to take what you might call a non-constant linear combination. That's a terrible abuse of the term, but sort of a non-constant multiply and add with those homogeneous solutions. Okay. All right. Okay, so we'll take this, plug it into there, see what the equation becomes. It becomes this. You'll notice the pattern. Here's that product rule thing again. Right? You'll recognize here's the previous, we already knew that M prime was equal to AM. We already talked about that because one column at a time. That just works. So in some sense, there's our old equation that we already had balanced. This new thing that showed up on the right that knocked it out of balance, I then tweaked my solution. The tweaking created this term. And so the hope is that, again, cancel these. The hope is then that I can just solve for V. Again, just like we did in the scalar case. And yeah, sure, it's no problem. You gotta, invert the matrix and take an antiderivative to solve for V. But there it is. There's V. V, keep in mind, that was the tweak. That was how you fiddle with your original solution's M, and therefore here finally is your particular solution for Y. So again, this works as long as the G is continuous. This is fine, which is great. Okay. All right, so let's see it in practice. I'm going to skip a lot of the algebra and arithmetic and such in executing this because there is a fair amount of algebra. So make sure you can fill in these blanks on your own. It's just, if you're going to use this on an exam, you've got to be able to fill in those blanks on your own, of course. But doing it here would just take up way too much time, and it's just algebra. I know y'all can do that. So okay, here is a non-homogeneous equation. Notice our right-hand side. All of a sudden, there's the old homogeneous equation. You might recognize it. There's our familiar matrix that we've done a lot with because it's awfully convenient to not have to redo eigenvector, eigenvalue arithmetic all over the place, right? So familiar differential equation. We already know that these columns are solutions, and therefore this is our matrix of solutions. Okay, we're just going to go through and play this game. We've got to take that M that we just found. We're going to invert it. We're going to multiply by G. We're going to take an antiderivative. And then we're going to multiply by M. It's a whole thing, right? But off we go. Okay. Okay, inverting the matrix. It's 2 by 2, so you can do this convenient trick where you just, y'all remember the convenient trick for inverting 2 by 2s? You switch the diagonal entries, you put minus signs on the off diagonal entries, and you divide by the determinant. It's a special case of that adjugate business from section 1.7. So, nice little convenient formula for 2 by 2 matrices. I encourage everybody to make sure you can remember that. Okay, so we inverted. Now we got to multiply by G. Here's our G. We got to multiply that times M inverse. That gives you, that gives you this. What do we do with M inverse G? Well, M inverse G, we have to take an antiderivative of. Okay. M inverse G, we're going to have to take an antiderivative. Notice we're taking an antiderivative of a vector. That means we're taking antiderivatives of both individual coordinates. Each one of those is an integration by parts problem. It's tedious, right? So I'm not going to spend time in class doing integration by parts. Y'all know how to do that. But that said, make sure that you are good at that kind of thing. Because, again, that's what's involved here. Okay. So there's that antiderivative. And lastly, we got to multiply that antiderivative times M, that original matrix that we had up there in the first place. And again, it's just a bunch of algebra, multiply, collect terms, etc. And there's your solution, and that is, in fact, a particular solution to the original non-homogeneous equation. Everybody okay? All right, the next example is not that different. The next example has one key difference. Here we go. You'll notice the same homogeneous part. Right? There's no reason to make that different. Our right-hand side now, though, has trig in it. And trig algebra can get ugly. We saw that back in chapter 4 when we were looking at gain and phase shift and that kind of thing, right? So the clever move that we pulled back in chapter 4 that we're going to rip off here is to say, let's look at this associated complex equation, right? Where the real part of this complex exponential right-hand side is the trig right-hand side that I had in my original equation. That being the real part of this, by a totally analogous argument that we made in chapter 4, that solution Y is the real part of this solution Z. So if we can solve this complex exponential equation, find Z, let's take the real part. Okay. Nice move. And with that in mind, same game. By the way, same homogeneous part. So the M in this question is the same as it was in the previous part. So there's the same M inverse. The next step is to multiply M inverse times G. There's the G. Multiply it out. It's a little trig. Exponential algebra. And you get that. That's what you have to take antiderivatives of. And hey, by the way, notice how not bad the integrals are. We're taking integrals of exponentials. They're just exponentials. I'm going to say among the easiest integrals ever, right? Maybe not as easy as polynomials, but it's right up there, right? They're really easy integrals. Boom, here they are. Up to it. It's nice. Yes?
So you have to solve for constants or anything
Yeah, no, the constants don't matter. In fact, if you look back at the original this equation here, here it is. If you had a constant in here, like let's put a plus C inside of here, plus C, right? That C would just get multiplied. I need another color. that C would just get multiplied by this M and give you a homogeneous solution. So that just turns into 0. Yeah, in the differential equation. Yeah. It's a great question. Thank you. So punchline, you don't have to worry about the C. Just kind of ignore it. It doesn't matter. Yeah. Right. Okay. So, so easy integrals. Don't forget what you do with the integral. With the integral, you have to then multiply that integral back by the M matrix, and out comes your solution. Now, there's a certain amount of algebra in there, but it's just the algebra of exponentials. And okay, I'll confess, there's a little bit of complex arithmetic, and that's, mildly annoying, but it's not that bad. Complex arithmetic in the big scheme of things, we've got a lot of tools, not that bad. Okay. That's your Z. Keep in mind, our strategy was once you know the Z, you just take the real part to get the Y. So taking the real part, kind of multiply it out and you get this. And there's that solution. What do you think? Everybody okay? Questions? All right, I think this is a good time to go back and speculate on what this problem would have looked like if we hadn't done this thing. If we had just said, phooey on that, I'm not afraid of trig, right? Let's plow forward with the trig. Let's see what this question would have turned into. Even with the trig, same M inverse. It's still the same homogeneous part, right? Okay. Multiplying by G would be different because we're no longer multiplying by that. We're now multiplying by cosine x instead of e to the ix. Right? And so this instead would be, it'd be negative 2/5 e to the negative 4x cosine x, and then 1/5 e to the 1x cosine x. So you'd have that. And at which point you say, hey, that's not that bad. Why? What's wrong with this? Well, look at the next step. The next step is I've got to take this thing and I've got to take its antiderivative. Right? This thing where, when we were dealing with just exponentials, complex, okay, to be fair, but nevertheless just exponentials, those were easy integrals, no problem. Again, super easy integrals, in fact. Now look what we have to integrate. Y'all remember how to integrate exponentials times trig functions? It's tricky. You have to integrate by parts twice for each one. That means, since there's, of course, 2 coordinates, you would have here 4 integration by parts problems. That's highly undesirable. Right? And not only is it effort and time you've got to put in on an exam to crank out all of the, oh my gosh, right? It's so much. It's also liability of the possibility of oops, make it miss a minus sign. It's so easy to miss a minus sign if you're doing integration by parts. Okay? So this is highly undesirable for integration by parts. Whereas instead, we could have 2 of the world's easiest integrals. I think that's highly, highly preferable. Right? Now, again, the cost here is complex arithmetic. But given the choice between a little bit of complex arithmetic versus 4 integration by parts problems, to me this is a no contest. I will take the complex arithmetic every time. For your consideration. Okay. Alrighty. Alright, now let's go back to the original example. Something weird happened in this original example. I didn't comment on it at the time, but I want to now. Let's look at this original differential equation that we looked at. It is what I'm going to call kind of simple in that the right-hand side there, it's just polynomials. Monomials, in fact, right? Just constants times x. Those are really easy functions. And then let's look at the solution that we ended up with here. The solution was just polynomials, first order polynomial, nothing scary at all, right? Just constants times x and constants. And fractions, but whatever. Structurally, we had a simple question with a simple answer, and yet the solution, how did you get from here to there, involved just lots and lots of exponentials. Right? So that seems suspicious. When you have an easy question with an easy answer, but a hard sort of way to get there in between, makes you wonder if there might not be an easier way. And in fact, there is. Asterisk. We'll come back to the asterisk. Let's solve that same differential equation again. Here it is. This time, I'm going to approach this differential equation kind of roughly 4.3 style, right? I'm going to say, hey, back in section 4.3, what did we do? We looked at our right-hand side and we said, that's just got certain terms of certain forms, and I speculate that the solution's going to be stuff that looks kind of like that, except for the fact that whatever I put in as my solution, I know that derivatives of that are also going to show up as terms, and I'll need stuff to be able to balance with those derivative terms. So roughly speaking, what we did in chapter 4 is we looked at the right-hand side, we started taking derivatives, and we just made note of what kinds of terms show up. And that was our guess. So let's do that here. Optimistically. Let's take this right-hand side. Notice what kinds of terms show up if you start taking derivatives. And let's call that our guess. I don't know if this is going to work. I mean, this is just a guess at this point, but we have a little bit of a precedent for being very successful with this strategy, right? So let's try it. Let's take this guess and plug it in. See what the equation turns into. And this resulting equation, kind of a vector polynomial equation, just like we do with lots of polynomials, when two polynomials are equal, their corresponding coefficients have to be equal. And so I can look, for example, at the constant terms. The constant terms here are, there's a constant term. There's a constant term. The constant terms tell me this. Now let's look at x terms. Okay, there's an x term and there's an x term, and that tells me this. So the constant terms have to line up, the x terms have to line up, and therefore I have two equations. And these are two easy vector equations. Solve for a and b. No big deal. It's easy to do in this case. Obviously, of course, I don't know b yet, so I can't solve for a yet. But once I solve for b, like so, I can take that b and use that to solve for a. And we're done. And it worked out really nicely. Right? How are we doing? Is everybody on board? Everybody see what happened here? We guessed. It worked. Okay. Alrighty. And last step, of course, once you know the A and the B tell you what your coefficients are in that form, and so our actual solution then is this. Okay, so you can see these numbers there and those numbers there. Okay, so let's consider our options now. Let's compare and contrast. Let's look at that solution that we just did. This was our undetermined coefficient solution, and you see it's pretty compact. That's all of the work. That's all there is to it. There's no integrals anywhere. That's nice, right? Alternatively, here's what it looked like when we were doing the big formula. The big formula that was guaranteed to work. And on the page, it doesn't look like it's that much more, but keep in mind, I skipped lots of details in here, right? There's two integration by parts in here that I just didn't write on the board. That's, for you to do on your own, right? So this is much more algebra It's got antiderivatives and exponentials. It's so much more going on in the solution compared to this much quicker, much easier solution. Okay, so what we have here is a choice situation. Your choices are, you can use the guaranteed formula that will always work, with the cost being that it is also always going to be a pain, right? So that's one way to go. Your other option is you can go this method, which is not guaranteed to work. Something might have gone wrong. Let's confess, we did guess here. It was a hope that this was all going to work out and that I could solve for the A and the B, and what if I can't, right? So there's a certain amount of a risk there. That's the cost, but look how easy. So you get to decide. My pretty strong preference is do it this way. Try it this way. Because most of the time it works. Right? And it's so much easier. Right? Now let me talk a little bit about what could possibly go wrong. Right? So, argument could be made, wouldn't this always work? Why wouldn't this work? Where it might go wrong is in these equations, when you're solving, notice that you do need to invert that matrix A. And what if A is not invertible? If A is not invertible, you might not have a solution for this B. In fact, you probably would not have a solution B. You might get lucky, conceivably, shot in the dark, right? But probably this whole thing would crash and burn if A is not invertible. Okay. All right. All right, here's another example. Different right-hand side here. Now we have, instead of x times a constant vector, here we have an exponential times a constant vector. What do we do in a case like this? Well, same strategy for guessing our solutions. What happens when you take this and start writing down derivatives? What kinds of terms show up as you differentiate that right-hand side? Well, they all look like this. Right? So our hopeful, not confident, but a hopeful guess would be that we try this form, and you take that and you plug it into the differential equation, and here's what comes out. You will find, by the way, as one of the algebraic steps, that there's a common factor of this exponential in all the terms. Cancel that common exponential factor. Move things around, and you end up with this equation. And again, all you need to do is solve for A. Right? A is our undetermined coefficient. You solve for it in this equation, and there you go. And, most of the time, that's going to work. And again, there's a risk that it won't, because there is a risk that A minus Ri, this matrix that you have to solve through, what if that's not invertible? And so that's a possibility, right? So, you got to worry about that. But, by the way, here's another way to say that. Under what circumstances would A minus Ri not be invertible? Well, that would mean that A minus Ri is singular, which means R is an eigenvalue. That's weird. So this condition, the worry is that R might be an eigenvalue. Okay. All right. I want to start the next example. We won't finish it. This is a really long example. It takes like 2 pages. But I want to address the question of what do you do if it is, right? So what if R is an eigenvalue for that matrix? How do you adjust your guess to hopefully recover from the otherwise catastrophe of this didn't work at all, and I still really, really, really don't want to have to use that great big formula several pages back? So here's the idea. Notice here, by the way, our old friend, this matrix, we've dealt with this matrix many times. We know the eigenvalues, we know the eigenvectors, and here this 4, that is an eigenvalue. So we are going to have the problem here, right? This probably won't work if I use the guess that I tried above. So how would we fix that? Well, here's our original guess. Constant times e to the 4x, e to the lambda x, Rx. we motivated that original guess by saying, okay, what happens when I start taking derivatives of my right-hand side? What kinds of terms show up? And, well, hopefully we can just make it balanced. Again, didn't work. So how do we work ourselves out of this? We're going to try to think up additional terms that I can add in. Here it is. Here's an additional term. And notice that if I add this in, then in the process of taking that derivative right there, we've got a product rule for this purple term here. This purple term, it's got a product rule thing going on, but one of the terms that will show up in the derivative, when I take the derivative of that x, will be another term with exponential times constant vector. So that dead-end equation that we found ourselves in here, I've got an additional term in there now, and that additional term will change this equation in such a way that hopefully we'll have the ability to actually make it work. So that's the strategy. And adding an extra term with a higher power of x very often gives you that potential. Okay. So we proceed just as before. We take this, we plug it in, we see what the equation becomes. The equation turns into this. Again, notice you have a common factor in each term of e to the 4x. Cancel that common factor. Great big expression involving vectors and powers of x. Group appropriately. Equate coefficients. And you get, again, two equations. I get this one and this one. And I need to solve for a and b. Okay, now we're not going to finish this example today. I just want to warn you about what we're going to have to deal with, and we'll actually deal with it next time. Monday, of course, is the exam. Don't forget the exam Monday. But by next time, I mean Wednesday's class. So here's the situation. It doesn't look like it's that bad. It seems like, well, this should work. In fact, let's look at this first equation. It seems like everything's coming up great because I can totally solve for b here. I've got a free variable. This is a singular matrix, so there's a missing pivot, so there's definitely a free variable, and I've got infinitely many solutions. Homogeneous, nothing to worry about. So it's easy to kind of get excited and say, my cup runneth over. I can pick any vector b, any multiple of whatever. I'm going to pick the easiest vector b because I like it when my life is easy. I'm going to pick one that has all integer coordinates, something like that. Right? Here's the problem. Yes, a minus 4i is singular, and that is helpful here. But a minus 4i is still singular in this equation. This one, not homogeneous. Now we have an existence problem. There might not be any solutions here. So don't make the mistake of picking b too early, willy-nilly, without thinking how you can use that flexibility that you have in your choice of b strategically to your advantage to try to turn this right-hand side into something that will have a solution in this equation. That's ultimately what we're going to do. It's not just pick any b. It's find a b that works here and that makes this possible. And there is a way to do that. It's a matter of thinking strategically and sort of writing things down, and we'll deal with those details next time. So y'all have a great weekend. Good luck studying for the test. See you on Monday.